So before we jump into the card game, I want to talk a little bit about what is complete information game and incomplete information games for those who don't know. So for complete information game, it's like chess that all the users know the full states of the game. And for incomplete information game, which is generally most of the card games, is that the users will have partial knowledge of the whole game states. However, for example, in game like Texas Hold'em, you will have your own hand cards that is hidden for other players. So basically have a partial information is called incomplete information game. So for the card games, they have its own problem. First is definitely privacy. So when it comes with centralized server that's dealing card, or like you can think about like all the card games server, they actually can see users' hands. So there used to be a scandal that GG Poker has its employee that basically log into the server and see others' opponent's card and make millions of dollars out of it. And mathematically, you can never know if that happens or not because it's centralized. And the second is the card shuffling algorithm. So this can be manipulated to either in favor to the house to make it like more addicted to the users or just make it less favor toward the users. And again, this is very hard to get it mathematically proved that it's fair because it is done through centralized server. So it's pretty obvious this problem, can be, like people want to solve this problem because there's a lot of people that love playing poker in crypto. However, as we all know, the data are saved publicly on chain, so it's very hard to do. And there's our attempted solutions using ZK. So curious, how many of you know mental poker? Nice, yeah. So ZK, this popular solutions implementing mental poker. Essentially, it doesn't even need smart contract to implement the core of it because it's based on the idea that all of the users in a P2P setting, they don't even trust each other. So locally, they do shuffling, card encryptions, and then they create a ZK proof for the above actions, and they pass all the cards around. And this action is a little bit different from FHE. It's called homomorphic encryption. So if me and like another two players are playing, the order that we done the encryption, shufflings doesn't matter. And for one card to get encrypted, shuffle, and dealt, it needs a multiple step, as you can see on the right. And that leads to an obvious problem with ZK solutions. The UX is very complicated. It needs multiple function calls for one user to get one card to decrypt and think about the delay when it comes to like networks, communications. And that's actually pretty hard. And also the time it required to generate the proof. So, and another thing is, if user actually drop out during the game, then that game is nullified. Say I'm playing with Alice and Bob, and then in the middle of the flop, Alice actually just quit, right? There's no way I can actually continue the game with Bob because I need actually Alice to get involved to continue the game. So I think that is impractical in reality, and here's the solutions. I think FHE can actually be better. So FHE provides first on-chain shuffle through the FHE random number generations. And second, the player's cards are only decrypted locally. So essentially, let's imagine a smart contract that has private data and it's an array of cards that is shuffled and that's encrypted. And when player accessing it, they are just using re-encrypt to access it. And another thing that can improve the performance, I'm gonna go deeper later on, is that the card shuffling doesn't have to be real time. I can have a bunch of decks generated upfront, and it doesn't affect the gameplay. So when it comes to deck shuffling, it's pretty straightforward for those of you guys who may already have coded in FHE. So basically how it works is generate a random number first. And then it check, to make it non-biased, we check if it's like bigger than a certain number since there is a certain number of cards. There's 52 cards for a poker game. We need to remove those that are bigger than that. And then we check if there's duplications in the DAX array, and if we add it to the DAX if it doesn't. For checking the duplications, it's basically looping through all the cards that we have generated through the random number generation. And then we return the total of duplication. So basically, if it returns 1, there is duplications. And if it's return 0, that means we are safe to insert the cards. So what we want to pay attention is that we don't want to decrypt during the for loop because it actually consumes a lot of gas. If we come back here, that it's actually more gas efficient if we check the duplications by just having one decrypt function call in the if statements, rather than in the for loop, and if there is actually a duplications, we just go out of the for loop by like just trying to decrypt for the every time when we iterate in the for loop. Any questions about that one? Nice. So when it comes with deal cards, generally there are two type of cards that are dealt. First is community cards. And as obvious as its name, it's cards that everyone knows. So it's basically, if you have a smart contract, you can just decrypt when the game states turn into like dealing the card, dealing community card, flop card, river card. And that's it's just as easy as by calling the decrypt in the smart contract. What's more interesting is the user's whole cards. So essentially, what can be done is that the user generate a public and private key pair, and then sign a signature, and using that perfect re-encrypt method from FHE. So basically, they do things like function read, but passing in their public key and signature and re-encrypt, and the function will return the re-encrypt ciphertext that is only available for the users to decrypt. So this actually provide a perfect solution that it's only the user that hold the public private key pair are able to actually see the card. And even though it looks a little bit complicated, like multiple step, the step 2, 3, and 4 are actually constant time. It's almost like reading a read function call from the contract. And for the first actions, generate the key pair, a user only need to sign once when they are entering into the game. So that actually is almost like a constant time for the users to do all the actions. One note is that for the decrypt function call, it's gonna turn into async pretty soon, or it's already there. So you may expect some change later on. So certainly there's still a way we should improve this performance. First is, as we mentioned earlier, is the deck shuffling can be done async. So we can have a server that's can keep generate. So basically, that server is basically that hold an EOA account that just keep calling the smart contract and generates and save the deck on chain. And then when the game starts, people can start like using the deck on demand. And the second performance improve is that we can have embedded wallets that remove the signing experience when people are playing bets or taking actions. So here's a quick video of what has come before and what comes after. So as you guys might see, I'm signing the signature to access my card. And yeah, it's a little bit brutal that I need to sign the signature every time. Yeah, so as you can see, this has some friction over there. And for after, once we have embedded wallet, so again, signing the signature to access card. the generated key pair and signing signature. And then yeah, so this experience is smoother with the embedded wallet experience. And I have 2 pairs over there, so which is pretty nice. So again, this version is fully on-chain. So there are still some challenge we are running into. The first is definitely the deck shuffling limit. So currently, actually, only 9 cards can be successfully generated due to the limits of FHE. And as you guys might notice, the card shuffling algorithm right now is a bit it's pretty inefficient, as you guys can see. So one solution that's pretty obvious is we need hardware acceleration. I think that's the main problem for all the FHE that people are envisioning. And the second is the software solutions. So for example, I think Theo from Inco proposed a solution about using delta swap, and that may lead to actually a constant time deck shuffling, and it's basically any number of cards can be shuffled in constant time. However, this may need to get more tested as it may be more biased when it comes to like 1 million hand generations, and it needs like more testing out. And the other is like trying using something like bit masking for duplication check rather than like for using the for loop. And the second is the speed. So right now, since this is a fully on-chain gameplay, the speed are bounded by the block time, which is almost unbreakable if users are playing the bet, and then they need to wait for about 2-second block time for the block to get complete. However, if we are thinking back, do we really need like to wait for the block time to get approved? So one proposed solution is we can keep the card shuffling and card dealing on chain. Well, the former card shuffling can be done asynchronously, and the card dealing is essentially just reading from chain, right? So it's not bounded by block time. And we make the more complicated gameplay off-chain. For example, hand evaluations, for example, like placing bets, taking actions. And then that leads to the problem of we need safe way to integrate the on-chain and off-chain part. And that is still unsolved right now. So here's the end game of how does it look like if we have that solved. So as you can see, this is just real-time poker gameplay, and it really wouldn't affect like, it's really just like real-time poker game now. Yeah, so to check out the demo, feel free to go to the FHE enable one, that's the link. And the partially centralized one, which is the endgame link I shows. Let me do the slideshow one more time. Yeah, and you can scan the QR code here. And if you have any questions or you are interested in discussing the technology, or you are just big poker player, feel free to reach out to me through Pokerr ETH or Julie Shi ETH. Or my TG. Yeah, thank you guys so much.
All right, any questions? Yeah. Welcome back. Thanks.
Thanks, Julie. Thanks for the presentation. Could you explain more what embedded wallets are, and are they the same as account abstraction or
Great.
something else?
Great question. So it's a little bit different. So account abstractions essentially are more for the gasless experience. So there's like paymaster that pay gas for you. But for embedded wallets, you can think of it as a temporary wallet, a session key that is created when you log in. So if you use, are you familiar with Privy? Yeah. So Privy, when you do social login, it creates embedded wallet for you. So it's basically a temporary wallet, and it's used for the gameplay. And it basically does the signing for you without you sign it. So yeah, does that answer the question? So like it's in the front end, it just basically low-key signing, clicking that sign button for you. But it just doesn't have the confirmation model show up.
So a follow-up question.
Well,
All right, so a follow-up question would be, does that temporary key hold funds also? Do your funds go to the temporary key funds?
Yes, so it does. For example, if you are playing a poker game, you join the table, and you temporarily have that fund like hold it by the session key. Yes.
anyone else? All right, let's thank our speaker again.